So on day 2 here, we're going to relate how our sequences relate to the change in linear and exponential functions. So if you guys remember, slope-intercept form was mx plus b. And what did we say our initial value was in this? We said it was b. Well, when we talked about arithmetic sequence, we said it starts with our 0 term plus our difference times n, where our initial value was a sub 0. And our constant rate of change is either m or our difference. So they're very, very similar when we're starting with our initial value. And you guys will remember, our y-intercept and then our slope up 1 over 2, up 1 over 2. So it's kind of like saying if we had a table and maybe it was 2, 4, 6, 0 goes with 2, 1 goes with 4, 2 goes with 6, and you had your line. And it's like that with our individual sequences, except our sequences are those discrete points. So we're not starting with an initial value. The one we talked about yesterday was you start with the k term plus d times n minus k. So let me write a sequence here to remind us. So let's say we had 3, 5, 7, 9. So if we were writing it before with our 0 term, we would go back and say, well, that's 1, and we're going up by 2. So our equation would be 1 plus 2x. If we were to graph this, our y-intercept is 1, and then our next term is 3, and then 5, and we can say our slope is up 2 over 1. Now, if we were to write it with any value, for example, if I started with the 7, I'd say we're still adding 2, but this would be 7 is our third term. So it would be n minus 3, because again, table form, 0 first term, second term, third term. Now you can write it similarly in point slope form too, where we can take any y value on the line plus our slope times x minus an x value that's on the line, where x1, y1 is just a point on that line. And this comes from our slope formula, because we know our slope is y2 minus y1 over x2 minus x1. Well, to get rid of our fraction, we just multiply by x2 minus x1 on each side. So now we have x2 minus x1, I could put the m out in front, equals y2 minus y1. And if we add that y1, it's similar to this right here. Now, geometric functions, our exponential is a times b to the x power, where a, again, is our initial value, and b is our common ratio. Well, it's similar as well, where g sub 0 is our initial term, r is our ratio. So again, a difference is that, we use n a lot when describing sequences, and functions we're using x. And again, a function, it's connecting those lines, where that sequence is those distinct points. Now our shifted that we talked about yesterday is super, super similar to what we did before, where we can where we could take any term. So I can take any y value times, I'm going to write a ratio this time, x minus x1, where again, that's just a coordinate on the line. Similar to that is a term in the sequence. But that big difference, again, these are those same graphs right here. One is a function, one is a sequence. A sequence is those discrete points, where the domain of the function, this is all reals because it contains every single x value there. Now what we're going to do is talk about how do we recognize the change between these. So again, there's a constant rate of change, but the difference is linear functions are based on addition and exponentials based on multiplication. So here's kind of the big terminology over equal length input values. And we've talked a little bit about that. If the output values of the change at a constant rate, then the function is linear. If it's changing proportionally, then the function is exponential. And so again, I sometimes have to turn these into tables. So I would say x, y, 2 goes with 1, 3 goes with 4, 4 goes with 16. And I bet visually you can see it's not adding the same thing. We're multiplying by 4, so it's exponential. So this next one, again, I tend to make tables because I can see things better. 5, 6 goes with 7, 7 goes with 10. Well, let's see. This is plus 4 plus 3, so it's not addition. And how would we figure out if it has a common ratio? Well, remember, our ratio would be 7 divided by 3. Well, is that the same as over here? 10 divided by 7, a term divided by 2 before. It's not the same, so this one would be neither. And then our last one, 3 goes with -1, 5, 7, 7, 15. Well, I can see, again, I should have checked these constant change. Going up by 2. Well, that's going up by 8, so it is linear. All right. If we know a function is either linear or exponential for sequences that would be arithmetic or geometric, then we only need these 2 points. So if we know f of x is a linear function and it passes through the points 3, 7, 8, 1. Well, we can always find the slope. We're getting really good at slope. Rise over run. So 1 minus 7 over 8 minus 3. So we have -6 over 5. And now we don't know our y-intercept, but we could use our equation, any y value, plus m times x1. So y equals, we could choose either y value, it doesn't matter. So 7 plus, and I guess I could go minus 6/5 times x minus 3. So again, these are, some formulas you will need to memorize. And then let's see, how could we do an exponential? So I know it goes through 2, 5. I don't know 3. 4 goes with 12. So how can we find our common ratio here? Because it's not slope. So I know I multiply by something, I multiply by something. So I could write the equation 5 times r squared equals 12. Because if I multiply by r twice, I end up with 12. Well, to solve this, divide by 5, divide by 5. So r squared equals 12 over 5. And then what do? I take the square root. So r equals the square root of 12 over 5. So now for our point, again, we can use our equation f of x, y1 times our ratio times x minus x1. So f of x equals, we could choose either point, I could do this, so 5 times the square root of 12/5 to the x minus 2. Again, very similar. It's like saying we know our second term, so we're starting with that second value. And this next part's pretty easy. Are these linear or exponential? Well, this is definitely exponential. And identify the constant rate or slope. Well, this would have a ratio of 2. What about this next one? Well, I bet you know it's linear. And what is our slope on here? Is 5. In the last part, again, we're going to identify linear exponentials, but you'll see it says justify. And that's the part that's going to take practice with the terminology. So I can see that these are going up 4. Well, what's happening here? It's going down 4. So it's going to be easy to say that this is linear. But your justification, we're going to want to acknowledge that each input change, and let's describe it as much as possible, of 4, that f of x changes, goes down by 4. So I'm acknowledging that we have equal value inputs, and we're saying what that change is. So our next one, we have equal value inputs going up by 2. And what's happening here? Well, I bet we can visualize it, times 3 times 3, so you can tell that it's exponential. But that description, so input, an input change of 2, f of x changes proportionally by a common ratio of 3. So as you can see, this is pretty similar to yesterday. There is one I want to go over on your homework, though, because I know you guys love fractions. So where was it? Maybe it wasn't on this one. Well, we'll give it a go. And if there's some where the fractions are driving you crazy, we can check in on those tomorrow.